could you please take seats? We are running a bit late. Okay. So it's my pleasure to introduce the first speaker of the second part of this afternoon session today. He's Dave Touchette from the University of Montreal, and he has won the Best Student Paper Prize of this year's QIP. And he will talk about he has simplified the title of his talk, which now reads Quantum Information Complexity and Direct Sum.
Thank you very much. So many thanks to the organizer for its great honor and for this great conference. So I will be discussing a problem in interactive quantum communication. So the setting is the following. Well, we're in a communication complexity setting, so we have Alice and Bob in distant labs. Alice is given some input x, Bob's given some input y, and they want to compute some function f of x and y, and they want to minimize the amount of quantum communication they have to exchange in order to do so. The amount of quantum communication they have to exchange. So we will take an information theoretic view on these quantum protocol, and this will lead to the notion of quantum information complexity, which mostly answers the question, well, how much quantum information must Alice and Bob exchange in order to compute f on some input distribution mu? So this is the main question that we will ask and answer in this talk. The results we obtain are the following. First, we introduce a new definition, a new fully quantum definition for quantum information complexity of quantum task. So, well, to keep it simple, we'll mostly consider task of the following form in this talk. So Alice and Bob want to compute some function f of their input x and y, where there's some prior distribution mu on this joint input, and we allow them some small probability of error in computing f. So, but in general, well, we can apply most of these results to like a more general tasks like computing classical relation and computing a fully quantum task. So we'll also prove an operational interpretation for quantum information complexity as the amortized quantum communication complexity. So this is the asymptotic cost per copy for computing many copies of a task in parallel. So we will also prove some important property of quantum information complexity. In particular, well, it gives an information theoretic lower bound on the quantum communication complexity for any given task. And, well, importantly, this gives such a lower bound independently of the number of message m in the underlying protocols. It also satisfies some additivity property. So for any two tasks, the quantum information complexity for computing these two tasks in parallel is equal to the sum of the quantum information complexity for computing the first task plus the quantum information complexity for computing the second task separately. So, well, with this property, a natural application for quantum information complexity is to obtain a direct sum result for quantum communication. So the direct sum question mostly has the following question. So can we gain anything by computing a given task n times in parallel in comparison to computing it, well, n times separately? So we'll use some protocol compression, which build on the recent one-shot straight redistribution protocol that we derived with Mario Berta and Matthias Christendal. And we obtained some direct sum result, which read as follows. So for m-round protocols, the quantum communication complexity for computing n times in parallel is at least n times the quantum communication complexity for computing this task a single time, up to some additional error. But there's also some multiplicative factor which depends heavily on this additional error term and the number of rounds in the protocol. So another potential application for this notion of quantum information complexity is to obtain tight lower bound in communication complexity. So this uses another property we prove for information complexity, which is that it satisfies a direct sum property on composite functions, which are built from simpler component function. So for example, for disjointness in terms of the n function. So the disjointness function can be viewed in the following way. So if we view Alice and Bob's input as sets, well, disjointness asks, are these two sets disjoint? So this can be computed as a negation of some big OR of the bitwise n of each and Alice and Bob input bit. So intuitively, well, you would think that to compute disjointness somehow requires you to, well, compute separately each of the bitwise n. And, well, quantum information complexity somehow enables you to formalize this, and we obtain a reduction from computation for disjointness in terms of n times computation of the n function for some input distribution. And this leads to the following conjecture. So we think that like the communication complexity, the quantum communication complexity for computing disjointness on n bit with n round protocol is at least n over m. So this would match the best known upper bound, which is n over m, and this would improve on the best known lower bound, which is n over m squared. So these are results which are known since 2003, and by the work of Aronson and Mbainis, and the work of Jane, Radhakrishnan, and Sen. All right. So, well, in this talk, I will mostly focus on, well, the justification and the intuition behind this new definition for quantum information complexity. And, well, from this intuition, well, a lot of these results follow quite naturally. All right, so before diving into interactive quantum communication, let's take a step back and consider unidirectional classical communication. So in this setting, we once again have Alice and Bob in the Inside Lab, and Alice wants to transmit some message M to Bob, and they only have access to some noisy communication channel. So, well, we can spread this further into the two prominent communication problem in communication theory. So first, before transmitting, Alice could try to compress her message if it has low information content, and then once her message is compressed, she will try to transmit it somehow noiselessly over a noisy channel. So in this talk, we'll be interested in the interactive quantum analog of this compression task, but somehow quite naturally, like we will, like noisy channel will enter the picture, but for the reverse task, so we will be interested in like simulating noisy channel, but over a noiseless channel. Good, but then the question is, well, how can we quantify information? So classically, a good measure of information is Shannon's entropy, which is defined as for some source x with distribution px as the average surprisal. So one of the reasons why Shannon's entropy is a good measure of information is, well, in particular, it has the operational significance that it is the optimal compression rate for Alice when she wants to transmit many copies of, well, many messages to Bob. So starting from the Shannon entropy, we can derive many other quantity, for example, conditional entropy, which has operational significance as the optimal compression rate when Bob has some side information y about the input. We can also derive the mutual information, which somehow characterize the noisy channel's capacity, but it also characterizes the reverse task of simulating a noisy channel over a noiseless channel. So this will be more important to us. Good. Now for interactive classical communication. So in this communication complexity setting, once again I have, well, Alice and Bob who have input x and y, and they want to compute function f of x and y while minimizing classical communication. So they will exchange sequence of message m1 up to mn. And we allow them to have some pre-share randomness r to like somehow minimize communication, but we also allow in this information setting Alice and Bob to have like private randomness. So SA for Alice, SE for Bob, SB for Bob. Well, then we will be interested in the notion of a transcript of the protocol. This is just the sequence of messages transmitted by Alice and Bob back and forth in the protocol. An important property of classical protocol that, well, we won't have the luxury to have in the quantum setting is that, well, this transcript somehow can memorize the whole history of the protocol in a classical setting. So since we don't have this in the quantum setting, this will be one of the reasons why it's so difficult to obtain a like quantum analog of information complexity. Okay, this leads us to coding for interactive protocol. So we would want to be able to compress protocol that do not convey much information. So we might want to do this when we have many copies of the protocol to compress in parallel, but we might also be interested in doing such a compression when we only run a single copy of the protocol. But then once again, like we have to somehow define what we mean by the amount of information which is conveyed by the protocol. So in analogy to what we somehow did in the unidirectional communication setting, well, we could try to define the amount of information in this interactive setting as the best asymptotic compression rate. So this leads to the notion of information complexity. So for some given task, information complexity is defined as, well, an optimization over all protocols that compute correctly for a given task of the information cost of this protocol, which is then defined as, for some protocol pi with input distribution mu, as the mutual information between Ali's input x and the protocol transcript, conditional on Bob's information y, plus the mutual information between Bob's input y and the protocol transcript, conditioning on Ali's input x. So, well, intuitively, this quantifies the amount of information that each party is going to learn about the other party's input from the transcript. So this satisfies many important properties. Well, first, it has the operational interpretation as being equal to the amortized communication complexity of a task. So that is, once again, the optimal asymptotic communication complexity for computing many copies of the task in parallel. So this was a result of Raman and Rao in 2011. So information complexity is a direct lower bound in communication complexity, independent of the number of runs in the protocol. It satisfies an additivity property. So for two tasks computed in parallel, the information cost is equal to the sum of the tasks computed separately. And it satisfies a direct sum property on composite function. For example, the disjointness function in terms of the n function, as we were stating at the beginning. All right. So, well, why is information complexity so important in classical setting? Well, it has found many applications recently. For example, for studying the direct sum question. So remember that direct sum asks, well, can we gain anything for computing many copies of a task in parallel in comparison to computing it like separately many times? Also has application in the related direct product setting, which has, well, once again, for computing n copy of a task in parallel, if we're only given access to n times the amount of resource that we need to compute a single copy of a task, well, thus the success probability decays exponentially in n. And also, quite excitingly, it has also found application recently to provide exact communication complexity lower bound. So for this disjointness function, it had been known for a long time. It had been known for a long time that, well, the communication complexity classically for disjointness is linear in n. But recently, using information theoretic tool, well, researchers have been able to pin down the first order constant term for disjointness. So now on to quantum communication. So a good way to quantify quantum information is with von Neumann entropy. So once again, it has an operational interpretation as the optimal quantum source compression rate. So we can define the right quantity in formal analogy to the classical one. But somewhat surprisingly, well, conditional entropy in the quantum case can be negative. But for mutual information, it still has the operational interpretation as a characterization of a channel is capacity in the entanglement assisted setting, and also for the reverse test. So with free entanglement, like the optimal channel simulation rate. Now on to interactive quantum communication. So, well, once again, we have Alice and Bob with input x and y. They want to compute a function f of x and y, and they want to do so while minimizing the amount of quantum communication that they will exchange in order to do so. So in the quantum setting, there's been many different models of communication complexity that have been defined. The first one was the model of Yao. So in this model, we do not allow for pre-share entanglement, but once the protocol starts, Alice and Bob can exchange quantum messages. A second model for quantum communication complexity was the one defined by Cleve and Berman. So in that model, we allow Alice and Bob to pre-share some arbitrary entanglement at the outset of the protocol, but once the protocol starts, they can only exchange classical messages. And we can also consider an hybrid between these two models, where we allow for both pre-share entanglement and for quantum messages during the protocol. Well, then we can ask, well, how can we define a notion of quantum information costs in this setting? So, well, we could try to formally copy like the classical definition. So for example, could try like quantum information cost could be the mutual information between Alice's input and the quantum transcript. So it would be the sequence of messages sent between Alice and Bob back and forth, conditioning on Bob's input, plus the amount of information between Bob's input and the sequence of message conditioning on Alice's input. Well, this doesn't provide a good definition for quantum information cost. So it has many problems. For example, in the Yao model, well, due to no cloning, we cannot even make copies of the sequence of messages, which are exchanged back and forth between Alice and Bob. So there's no real quantum analog of notion of transcript, which keeps somehow a copy of each message exchanged in the protocol. So since we can only evaluate information quantity that are defined at the same moment in time, well, this notion is not even well defined in the Yao model. However, in the Cleburne model, well, messages are classical, so at least this is well defined. But we still have some big problem here. So these messages could be completely uncorrelated to the inputs. So in particular, in the protocol where Alice and Bob just teleport back and forth to each other, well, the sequence of classical messages that they exchange will be completely uncorrelated to the inputs. So this notion will evaluate to 0, so somehow useless. So some potential solution to this would be, well, to try to take a different look on the classical notion. So the classical notion is this mutual information between the input and the transcript somehow accumulates all the information exchanged during the protocol. So we could try to do something similar quantumly. Just accumulate as much information as possible and keep it till the end, and then evaluate the mutual information on it. But a problem with this notion would be that quantumly computing a classical function, well, there are reversible protocols that do not produce any garbage. So for example, they can generate the output and, well, reset everything else to as it was at the beginning. So like the input is reset to as it was, the pre-share entanglement, so on. So for binary function, for example, the information that's left at the end of the protocol is bounded by one, by constant. So this yields another trivial definition. So this is not an interesting notion, but, well, it's not because there's not much information left at the end of the protocol that there hasn't been a lot of information exchanged back and forth between Alice and Bob during the protocol. So somehow we could try to instead measure how much correlation there is at each time step. So an example of a way to do this would be to, well, take each round in which Alice communicates to Bob and measure the mutual information between Alice's input and Bob's register after receiving Alice's message, and then condition on the information that he already had in his input, and then add this with the sum of like the mutual information in each round in which Bob communicates to Alice of the mutual information between Bob's input and Alice's register after receiving this message. So this yields an interesting notion of information cost that's already been, well, variation of this has already been used, for example, in the paper by Jane, Christian, and Sen, to obtain a lower bound on bounded rod complexity for disjointness function, and more recently by Jane and Yak for some other lower bound purpose. But one of the drawbacks of this notion is that, well, for a protocol in which there are m messages exchanged between Alice and Bob, and total communication C, this notion of information cost could be as large as m times C. So in order to get an information theoretic lower bound on communication, we first have to divide by the number of rounds in the protocol. And remember that, well, we want a direct lower bound on quantum communication complexity, which is independent of m. So the approach we take instead is to reinterpret the classical information cost. So let's take the following view on classical protocol. So once again, we have Alice with her input x, Bob with his input y. They pre-share some randomness r, but in this information setting, Alice also has access to some private randomness SA, Bob has access to some randomness SB. And then once the protocol starts, well, Alice generates the first message by taking, well, as a function of her input and also of the randomness she has, transmit this to Bob. Then when Bob receives this, he generates the second message by considering this new message, his input along with his randomness, and so on. So nothing new there, but, well, notice that in these messages, we're not interested about the information that they contain about the randomness. We're only interested in the information they contain about the inputs. So like any information about the randomness is somehow noise here. So Alice and Bob share the randomness R. So somehow they can account for this. But the private randomness really looks like this, so complete noise. So somehow this message generation process can be viewed as a noisy channel. And well, we'll take this view that the protocol is just a sequence of like a noisy channel simulation. All right, thanks. Good. So in order to somehow do not communicate this this noise information, well, we'll allow Alice and Bob to share some more randomness, and Alice and Bob will somehow sample the noise in the channel from this shared randomness, so they won't have to communicate it. So this will allow them to like reduce the amount of communication. So for this test, the asymptotic cost was already known, and it's given by the mutual information between the input distribution and the output message M, conditional on the side information that the receiver is. So if we take somehow the intuition as for unidirectional communication, that well, the asymptotic communication cost should be a good measure of how much information is contained in the message. Well, the sum of the asymptotic channel simulation cost here should be a good operational measure of how much information is contained, well, is conveyed by the protocol. And then if we just rewrite this sum of asymptotic channel simulation costs, and well, apply some channel and so on, it's exactly equal to this previously defined notion of information cost. So it somehow gives an intuitive new proof that the information complexity is equal to the amortized communication complexity. That's also preserved the run complexity. All right. So now for quantum interactive quantum communication, well, we can also quite naturally like extend this noisy channel simulation view for quantum protocol. So just consider like every message generation as some noisy channel, and we'll take the purified view for everything. So just purify every channel by seismometric extension, and well, the environment will now be given as feedback to the sender. So the correct task to consider in this setting is quantum channel simulation with feedback and side information at the receiver. So this is equivalent to the quantum state redistribution task, but it's just abstracting away this noisy channel. So in state redistribution, we have Alice and Bob, and Alice wants to transmit some register C to Bob, and she has some side information A about C. Bob has some side information B about C, and well, the ABC register are purified by the R register, some R register. And the asymptotic communication cost for this was already known. It's given by the mutual information between the purifying register and the communication register, while conditioning on the side information at the receiver. So if we, well, once again, extend what we did in classical setting and take this asymptotic channel simulation view, well, a good operational measure of how much information is conveyed by this quantum protocol is just the sum of the asymptotic channel simulation cost. So this yields the new notion of quantum information complexity, and that also naturally yields the Cloning theorem that it's equal to the amortized quantum communication complexity. Moreover, well, we can show that it satisfies all of the other properties that we stated as desirable for an information complexity measure, and it also yields the first general multi-round direct sum result for quantum communication complexity. Right. So well, let me conclude with a summary of the results. So we provided a new definition of quantum information complexity, which satisfies the desirable property that we want for an information complexity measure. Provided an operational interpretation for it as the amortized communication complexity, and provided an application to a direct sum theorem for bounded round quantum communication complexity. All right, and so there's still a lot of interesting open question in this research program. So do I still have some time? Oh, great. Okay, great. So well, first interesting question to look at would be to try to obtain tight communication complexity lower bound. So well, is it possible to build on the work of Jane Radcliffe and Sen and obtain a tight lower bound for bounded round quantum communication complexity of the disjointness function, and well, for other functions which are built from simpler component function. Also, well, the notion that we define here is somehow a notion where there is some prior input distribution or some prior state that we want to measure quantum information on. So is it possible to find some prior free version of quantum information complexity? Also, well, it would be interesting to see if we can get some general upper bound on quantum communication complexity in terms of quantum information complexity, which doesn't depend on the amount of the number of rounds in the protocol. Sorry. So also, can we see which lower bound for quantum communication complexity would also apply for quantum information? And other than that, well, it's been shown recently that in the classical setting, there's the exponential separation between information and communication for some tasks. This is a recent result by Ranraz and Cotter. So, well, would this extend to the quantum setting? And well, also obviously, well, it would be interesting to see if we can get much improvement on like direct sum result, both in this bounded round setting and also in the arbitrary round setting. And can we further extend this to obtain a direct product theorem, even for a single round and product distribution maybe? So thank you very much for your attention.
Thank you very much for this nice talk. Are there any questions or comments?
So I guess one of your goals was to prove this lower bound for disjointness, which would be of the form n divided by the number of rounds plus the number of rounds. Exactly. Can you say what is the obstacle there to achieve that bound?
Well, at first was the fact that this quantity is defined in terms of like a fully quantum conditional mutual information. The question was, well, one of the original goal was to try to obtain some tight lower bound on like bounded round disjointness of the form, well, omega of n over number of round plus number of round for communication. And well, one of the obstacles there was the fact that this information notion is defined in terms of like a fully quantum conditional mutual information, which is known to be really hard to lower bound. Like even like strong additivity, which says that it's a non-negative quantity, is a really useful result, which has been really hard to prove in information theory. But well, there's been some recent development on lower bounding this quantity, Fuzzian rather, and well, at first it seemed that it's quite useful here. Well, it can be useful, and you can obtain some lower bound. It's just that it's not better than the previous one. But somehow you would think that you're getting the lower bound that you want at first, but the reduction that I discussed at the beginning like only works for input which have support like for the n function on on input that maps to 0 somehow. So you then have to like apply an hybrid argument to also say something about what happens for these protocols, which are good on all input, what happened on the 1-1 input. And it's somehow when you try to go from like these input that map to 0 to this 1-1 input that you're losing something. Well, maybe you don't have to lose something. It's just that for now that's where it's stuck.
We have time for one more question. Cool. Well, if this is not the case, I suggest we thank Dave again.
Thank you very much.